Good day, everyone. Welcome to our lecture on database technologies. Today, we will delve into a fundamental and highly practical topic, CRUD operations in MongoDB. This lecture will serve as a comprehensive guide to creating, reading, updating, and deleting data using the pymongo library in a Python environment. We will cover everything from the initial setup to executing complex queries. Let's outline our agenda for today. We will begin by defining the acronym CRUD and understanding why these four operations are the cornerstone of data management in any persistent storage system. Next, we will proceed with the essential prerequisites, setting up our environment. This involves installing the pymongo driver, which is the official Python library for MongoDB, and configuring network access in MongoDB Atlas to allow our application to connect to the database cluster. Once connected, we'll dive into the practical part, starting with create operations. I will demonstrate how to insert a single document using insert one and how to efficiently add multiple documents in a single batch with insert many. Then we'll move to read operations. We'll learn how to retrieve a single document with find one and multiple documents using a find query, which returns an iterable cursor. We will also explore how to build more specific and powerful queries using various operators. After reading data, we'll cover update operations. You will see how to modify a single document with update one and perform bulk modifications with update many, using essential operators like set to change values, inc to increment numbers, and push to add elements to arrays. Following that, we will address the delete operation. I'll show you how to safely remove a single document with delete one and multiple documents using delete many, emphasizing the permanent nature of this action. Finally, we will summarize the key methods covered and discuss a crucial best practice, properly closing the connection to the database to ensure our application is robust and efficient. So, what exactly is CRUD? This acronym represents the four fundamental operations that are essential for any application that needs to manage data. Create is the first operation. It's the function of adding new information to our database. For instance, when you sign up for a new service, a create operation adds your user profile to their system. Read is the second operation, and it's how we retrieve data. When you log in, the system reads your profile information to load your homepage. When you search for a product on an e-commerce site, you are performing a read operation. Update is the third operation. It allows us to modify existing data. Changing your profile picture or updating your shipping address are classic examples of an update operation. Finally, delete is the fourth operation, which permanently removes data from the system. When you delete a post from your social media feed, you are executing a delete operation. Essentially, almost every interaction you have with a modern application, from a simple mobile app to a complex enterprise system, can be broken down into one or more of these four CRUD operations. Mastering them is the first step to becoming proficient in database management. The first step in our setup is to install the pymongo driver. Think of a driver as a translator. It allows our Python application to send commands and receive data from the MongoDB server, converting everything into the appropriate BSIM protocol that MongoDB understands. To install it, we use the standard Python package manager, pip. I want to draw your attention to the SRV part. This is not optional when you are working with MongoDB Atlas. It automatically installs another helpful library called NoSQL, which is required to correctly interpret the modern MongoDB plus SRV connection strings that Atlas provides. This format simplifies connecting to complex database systems like replica sets. Once the driver is installed, we need to address network security. By default, your MongoDB Atlas cluster is isolated from the internet. To connect to it, you must explicitly grant access to your application's IP address. Now, this presents a challenge for environments like Google Colaboratory, which don't have a single static IP address. The virtual machines are assigned dynamic IPs from a large pool. Therefore, for our purposes, the most straightforward approach is to allow connections from any IP address. To do this, you'll go to your Atlas dashboard, find the Network Access tab under Security, and click Add IP Address. In the dialog box, select Allow Access from Anywhere. This will pre-fill the entry with 0000/0, which is a notation representing all possible IP addresses. I must stress that while this is convenient for development, it is a significant security risk in a live application. For a real-world project, you would need to restrict this list to only the specific known IP addresses of your servers. With the setup complete, let's establish a live connection to our MongoDB cluster. The first step in our code is to import the Mongo client class from the pymongo library. This class will manage our connection. Next, we need our unique connection string or URI. You can get this directly from the MongoDB Atlas user interface. It's a single string that contains all the necessary information to connect: your username, password, and the unique address of your cluster. For security reasons, it's highly recommended not to hardcode this URI directly in your script in a real-world application. Instead, you should use environment variables or a secure configuration file. We then create an instance of the Mongo client by passing our URI to it. This object represents our connection to the database. Finally, to ensure everything is working correctly, we include a verification step. The try, except block attempts to send a simple ping command to the database server. If the connection is successful, the server will respond, and our script will print a confirmation message. This is a simple but very effective way to confirm that your application and database can communicate before you start trying to read or write data. Now that we have a client connected to our cluster, we need to specify which database and collection we want to work with. The syntax for this in pymongo is very intuitive and looks just like accessing a Python dictionary. Here we are selecting a database named University and, within that database, a collection named Students. An important concept to understand with MongoDB is what's called lazy or implicit creation. When you execute these two lines of code, nothing actually happens on the server. You won't see a new database or collection appear in your Atlas dashboard just yet. MongoDB waits until you perform your first write operation, like inserting a new student record, and only then does it physically create the database and collection on the disk. This is an efficient approach that prevents the creation of empty, unused database structures. Now let's perform our very first write operation. We will add a single document to our students collection using the insert1 method. The first step is to define the document we want to add. In the world of Python and pymongo, a MongoDB document is simply a Python dictionary. Here you can see we've created a new student dictionary. The keys of the dictionary, like name and student ID, become the field names in the document. The values can be of various types, including strings, numbers, and even arrays or other nested dictionaries, which you can see in the grades field. Next, we call the insert_1 method on our collection object, passing the new student dictionary as an argument. This sends the data to our MongoDB server, which then writes it to the collection. The method returns an insert1 result object, which we've captured in the result variable. This object contains useful information about the operation, most importantly the inserted ID. This ID is a unique identifier or primary key that MongoDB automatically generates for every document if one isn't provided, ensuring that every document in a collection is uniquely identifiable. In many real-world scenarios, you'll need to add more than one document at a time. For this, pymongo provides the insert many method. The key difference is that instead of a single dictionary, this method takes a list of dictionaries as its argument. As you can see in the example, we've created a new students list, where each element is a complete dictionary representing a student. The primary advantage of using insert many is performance. Instead of making a separate network request to the database for each document, it bundles them all into a single request. This significantly reduces network latency and is much more efficient for bulk data insertion. After the operation completes, the returned result object contains an attribute called inserted IDs, which is a list holding the unique ID for each of the documents that were just added to the collection. Now we move to the read operation, which is all about retrieving data from our collection. The simplest way to do this is with the find_1 method. As its name implies, this method is designed to find and return just a single document. If you call find_1 without any arguments, as shown in the first example, it will simply retrieve the very first document it finds in the collection. This is useful when you just want to quickly inspect the structure of your data, I'm also using the print library here for pretty printing, which formats the output to be much more readable. However, the real power of Find One comes when you provide a query filter. A query filter is just a Python dictionary where you specify the criteria for the document you're looking for. In our second example, we're looking for a document where the studented field is equal to KHNU2023001. Pymongo then searches the collection and returns the first document that matches this condition. A crucial point to remember is that if Find One doesn't find any document matching your filter, it will return the special Python value none. Therefore, it's always a good practice to check if the result is none before you try to work with it, to avoid potential errors in your code. When you need to retrieve more than one document, you use the find method. This is one of the most common operations you'll perform. The important thing to understand about find is that it doesn't return a list of documents directly. Instead, it returns a cursor object. You can think of a cursor as a pointer to the results of your query, which are still sitting on the database server. This is a very clever and memory-efficient design. Imagine if your query matched 1,000,000 documents. Loading all of them into your application's memory at once could cause it to crash. With a cursor, you can simply loop over it as shown in the for loop, and it will fetch the documents from the server one by one, or in small batches. In our example, we're creating a query filter to find all documents where the year field is 3. The find method returns a cursor. We then iterate through this cursor, and with each iteration we get the next student document, which we then print. If you wanted to retrieve every single document in a collection, you would simply call find with an empty dictionary as the filter, like this, collection.find. So far, our queries have been simple equality checks like finding a document where the year is exactly 3. But what if we need to find students in their 3rd year or higher? For this, we use query operators. These operators, all starting with a $sign, give us the full power of comparison logic. As you can see from the table, we have operators for not equal, greater than or equal to, and so on. A particularly useful one is in, which allows you to check if a field's value matches any of the values in a list you provide. For example, you could find all students majoring in either computer science or cybersecurity with a single condition. We will now see how to combine these operators to build even more powerful queries. Now let's combine these concepts. A common scenario is needing to query a value that's nested inside another structure. In our student documents, the grades field is an array of smaller documents, each with a subject and a score. To access the score, we use dot notation, grades.score. This tells MongoDB to look inside the grades array and inspect the score field of the documents it contains. In this example, we build a query with 2 conditions. The first uses the any operator on the year field. The second uses dot notation and the GT operator on the nested score field. Because we've placed both of these conditions in the same query dictionary, they are implicitly joined by a logical AND. This means the query will only return documents that satisfy both conditions. The student must not be in their 3rd year, and they must have at least one grade of 95 or higher. We now arrive at U4 update, which is about modifying existing data. A critical rule in MongoDB is that you don't update a document by sending a whole new version of it. Instead, you use specific update operators to tell the database precisely which fields to change and how to change them. This is a powerful feature. It minimizes the amount of data sent over the network and allows the database to perform these changes atomically and efficiently. Let's look at the most common operators. Set is what you'll use most often. It sets the value of a field, creating the field if it doesn't already exist. Unset is its opposite. It completely removes a field from a document. Inc is a handy atomic operator for incrementing or decrementing numbers. And finally, push and pull are essential for working with arrays. Push adds an element, and pull removes elements that match a specific condition. Now let's apply what we've learned using the update one method. This method, as its name suggests, is used to modify a single document. It takes 2 essential arguments. The first is the filter doc, which is a query that identifies the document you want to change. In our example, we are looking for the student with a specific student ID. The second argument is the update doc. This is where we use the operators we just discussed. Here we use set to add a new field, email, to the selected document. After executing the command, pymongo returns an update result object. This object is very useful for verification. Its matched count attribute tells you if your filter found anything, and modified count confirms if any changes were actually made. As you can see, we print these counts and then use find_1 again to retrieve and display the document, confirming that the new email field has been successfully added. Just as we can insert many documents at once, we can also update many. For this, we use the update many method. This is extremely useful for applying the same change to a large number of documents that share a common characteristic. The syntax is identical to update one. It takes a filter and an update document. The crucial difference is in its behavior. It will find every document that matches the filter and apply the update to all of them. In this example, we have a scenario where a new subject needs to be added to the records of all third-year students. Our filter is simple. Year equals 3. For the update, we use the push operator, which is designed specifically for adding elements to an array. We are pushing a new embedded document representing the new grade into the grades array. After execution, the update result object will show us how many students were matched and how many of their records were successfully modified. This single command is far more efficient than fetching each document, changing it in our application, and saving it back to the database one by one. We have now arrived at the final letter in CRUD. D for delete. I want to start with a strong word of caution. Delete operations are permanent. Once you remove a document, it is gone for good unless you have a backup of your database. Always double-check your filters before executing a delete command. The delete one method is straightforward. It takes a filter document as an argument, finds the very first document that matches it, and removes it from the collection. In our example, we are targeting the student with the student ID K2023003. We pass this filter to delete one. The operation returns a delete result object, and we can check its deleted count attribute to confirm whether a document was found and deleted. It will be 1 if the operation was successful, and 0 if no document matched the filter. To be absolutely sure, we can try to find that same document again, and as expected, the result will now be none. The delete many method works similarly to update many. It takes a filter and removes every single document in the collection that matches it. This is incredibly powerful for bulk data removal. To make our example practical, let's first imagine we need to mark a couple of students as inactive. We can do this with update many. Now that we have some data to target, we can proceed with the deletion. Our filter is simple. Status: inactive. When we pass this to delete many, it will find all documents with this field and value and permanently remove them. Again, the deleted count attribute in the result will tell us how many documents were affected. I want to repeat the warning. Be incredibly careful with this command. If you were to call collection delete many with an empty filter, it would wipe out every single document in your collection. Always be certain of your filter before you run a delete_many command. To help solidify what we've learned today, let's go over a few key questions. First, think about the difference between find one and find. Remember, find one returns either a single document or none, while find returns a cursor object. The cursor is memory efficient because it doesn't load all the matching documents into your application's memory at once. Second, the update operators. We must use them to tell MongoDB precisely how to change a document. If we didn't, the default behavior would be to completely replace the existing document, which would likely cause unintended data loss. And third, lazy creation. This simply means that MongoDB doesn't create a database or collection when you first reference it in your code. It waits until the very first document is written to that collection, and only then are the structures physically created. I encourage you to review these concepts. You can find a more extensive list of questions in your lecture materials to fully test your understanding. That concludes our lecture on CRUD operations in MongoDB. We have covered the fundamental building blocks for interacting with a NoSQL database, from creating and reading data to updating and deleting it. Mastering these skills is essential for any developer working on modern, data-driven applications. If you have any further questions as you review the material, please feel free to reach out via email. Thank you all for your attention.